All right, so we'll go ahead and get started. So today's recitation is a follow-on from 2 weeks ago, where we started our talk on attitude or orientation. So this was before spring break, so it's been 2 weeks. And there I kind of laid out a bunch of stuff with rotation matrices and direction cosine matrices. Today we're going to finish all that off and talk a lot more about quaternions and everything we need to know for this class specifically and doing the homeworks. So with that, the first thing we'll do is we'll just do a quick run-through of review of Recitation 7. And then we'll do quat math. Zach has his own way of not doing the quaternion math, but like how we actually like write it out. So the math is the same, but the notation is a little different. So we'll go over that. And then we'll do just a nice kind of review chart of everything between quaternions and the direction cosine matrix, which again is the rotation matrix. All right, so actually before I do any of this, I'm gonna take one quick second and I'm gonna go over some quiz stuff. Because we had some like somewhat surprising results on the last quiz. Okay, so the first thing we'll do is we'll do just one quick aside on quiz stuff. So a lot of the people's issues with the quiz comes down to how well you understood the capabilities, limitations, and expectations, I guess, when we use a non-convex solver like SNOPT or IPOPT. So again, if I have min f of x subject to c of x equals 0, g of x less than equals 0. Okay, and I say any. So if any of these are non-convex, so if any of these are non-convex, our whole problem is non-convex. So if the cost function or any of these constraints. And so let's go over, I guess, just like our expectations of what we do when we send things off to a solver. So expectations. So here on the left, we'll do convex. And on the right, we'll do non-convex. And we'll do a little. Let's move this over. The point I'm about to get at like should be very clear by the end of this. But because we do so much non-convex, nonlinear stuff in this class, it's easy to get comfortable with, I guess, that term and that idea, but we should really know just how dangerous this is. So, okay, so the first expectation is it always solvable? So guarantee of global solution. So with the convex optimization problem, we have this guarantee that if a global solution exists to the problem, I can find it. So this is like one of the great things about convex optimization. If there's a global solution out there, I can find it. Non-convex, I do not have that guarantee. And so let's go to something a little weaker. So guarantee of a local solution. Guarantee of local. So again, convex problems, any local minima is a global minima. So because we have a guarantee that we'll find the best solution ever, we will definitely find a locally optimal one because anything that's locally optimal is globally optimal. And then now we go to non-convex. So actually with non-convex problems, we have no guarantee of even finding a local solution. And this is like a big deal because This is the least you could ask for from a solver, is that like give me a local solution, and it wouldn't be able to do it. Next thing is, and this one's a little nuanced, but this is find a feasible solution if one exists. So if I have a bunch of crazy constraints, my convex solver, no matter what they are, as long as it is like theoretically solvable, this thing will solve it. Now with non-convex problems, again, I have no such guarantee. Even if a feasible solution exists, there's no guarantee that I can actually get this thing, which is scary, right? And this leads us to our last kind of main distinction, which is we get a solution in let's see, best way to say this. So we have, it's in polynomial time. So we have a known complexity of solving convex problems. So a way to think about this is we can get a solution in a reliable amount of time. So if I'm using an interior point method, I can say I will get a solution within 20 iterations. And there's certain algorithms which I can guarantee that. And with more performant algorithms, I will always beat that. So I have something that will tell me what is a reasonable amount of time it should take to solve this problem, and I can find it in that time. Again, convex problems can do it, non-convex can't do it. So this should be like pretty stark. Basically, like non-convex optimization is like the Wild West of optimization. We have no guarantees for anything. There's no guarantee we find the global solution. Definitely not, because that's the hardest thing to do. We can't even guarantee that we're going to find a local solution. Sometimes it just won't converge to anything. There's no guarantee that we find a feasible solution, even if one exists. So for instance, a really easy example to demonstrate this is imagine if I gave Dirkall, like what you guys just did for your homework, for question 1 of homework 3. If I gave you Dirkall as a general solver architecture, and I said, I want you to solve this maze problem, and I wrote out the constraints of a maze, and I said, get from A to B. There's no guarantee that's going to figure out how to get through the maze. That would be insanely impressive if you could do so. So I don't even have a guarantee that this thing will find a feasible solution if one exists. And the last thing is that for convex problems, I basically have a nice bound on how long it should take to solve this problem with certain algorithms. So for instance, with interior point methods, these are well known for being polynomial time in the problem complexity. So I know how long it should take me to get a good solution. With non-convex problems, you have absolutely no idea. It could take 100 iterations. It could take 25,000 iterations. Like there's no way to know how long it will take, and there's no guarantees it'll take a certain amount of time. So with that, I just kind of went on a bash fest over non-convex problems. That being said, we still use them all the time. So anytime we use like iterative LQR, we're solving a non-convex problem because our dynamics are nonlinear. So we're going to do all sorts of stuff in this class, and we already have done lots of stuff in the homeworks where we're solving non-convex problems. And it's fine. Like we can do it. And oftentimes where we initialize makes a really big difference. So maybe another nice thing to add here is that initialization doesn't matter for being able to solve. So basically saying like, does it matter how well I initialize? So for convex problems, it doesn't matter. We don't have to initialize this as anything. We can choose to warm start our problem to maybe get it to solve a little bit faster. And a lot of the more modern solution methods, specifically first order methods, they love warm starting, and often you can get pretty big time savings if you warm start nicely. But you don't need to initialize well to guarantee you can solve. If it's solvable at all, the solver will find it. Non-convex problem, this like I'm gonna see how many X's I can possibly put here. This is like the most important thing, is that the initialization is so incredibly important. You can take a problem and you can initialize it one way and it will converge in 10 iterations. And you can initialize it another way, it'll take 25,000 iterations. Like how you initialize is everything for non-convex problems. And this is true with general like nonlinear things. Using Newton's method on a bad initial guess oftentimes ends up with no solution whatsoever. We have to kind of start in this what we call basin of attraction. And the same is true for non-convex problems. Again, we're like this is the total Wild West. There's no guarantees of anything. Basically, non-convex optimization is gnarly. The solvers are gnarly, the expectations are low, if any. But in practice, it actually works okay. And if we are very smart about how we initialize and that we don't set up problems that are too crazy, oftentimes you can get non-convex optimization to do some pretty cool control stuff. For instance, all of your homework 3 was you guys doing non-convex stuff, and hopefully you got some cool results. Okay, so any remaining questions on convex versus non-convex? Hopefully this is a pretty stark, pretty scathing indictment of non-convex problems. So. And I think we'll probably ask a few more questions like this on the next quiz because this is, I would argue, one of the bigger takeaways from the class. Uh, I'd imagine if you were being interviewed for a role where you were expected to have some sort of optimization background, these are like very common questions that you would get asked because understanding like what you can and can't do is pretty maybe almost more important than knowing how to do it. Okay. So there, that concludes our quiz discussion. And again, I'll just like all the weeks, I'll put up the quiz solutions. You can look through them if you want to. So now let's do a pretty quick run through over what we did last or 2 weeks ago in recitation. So we started out by talking about vectors as this abstract quantity. It's a physical quantity. So it's just something with a magnitude and a direction, doesn't have a basis yet. And if I want to express it in some basis n, I take the dot products of A with all of my unit vectors for the n basis. So I take A dot nx, A dot ny, A dot nz. And once we establish this idea of kind of like an abstract vector and what that dot product means, which is just the norm or the magnitude of both vectors and then the cosine of the angle between them, we then introduced what the rotation matrix, or what I like calling it, is the direction cosine matrix. And the reason I like calling it the DCM or direction cosine matrix is because it really is not rotating anything. It's just telling you the way that these two unit vectors line up. So if I have a bunch of n vectors and a bunch of b vectors, my direction cosine matrix really just stores all 9 dot products. And then what's nice about this is that because each of these unit vectors is norm 1, it really is just the cosine. So it's just a bunch of cosines between all these angles. And that tells you everything you have to know about the orientation relative of these two bases. And then we also said that these matrices are special. Quite literally in the name, they're special. SO3, so it's has a nice determinant equal to 1, always positive 1. It's orthogonal, so the inverse is just the transpose of it, which makes sense given the way that we actually constructed this thing. And 3 because it's a 3 by 3 matrix. And the way we use this is that we'll take some vector A as it's expressed in the B frame, and we multiply it by this, and then we get this as expressed in the N frame. And something I didn't mention that is actually probably worth looking into it is that if you go take this as it's represented like this and multiply it by this, and what you'll see is that all these dot products cancel. And they all cancel, and you end up with like exactly what you think you would. So this is a nice exercise to go do, is go actually like write this out with all the vectors and see that it actually works. Okay, then we talked about how to compose attitudes. So if I have, a world frame, then an A frame, B frame, C frame, I can just link these things up with matrix multiplication, works super well. I also talked about how we can transpose this, and the same way that we transpose a chain of matrices being multiplied, we do the same thing and everything works out. So nothing should surprise us yet. Then I made a point about how there's just some absolutely terrible notation out there, which I like really stand by and will argue with anybody about. We now have a skew or cross product matrix or hat map, all kind of the same. Sometimes you'll even see tilde, but it's just the idea of taking this vector and converting it into a 3 by 3 skew symmetric matrix where we just pull out the components like this. And the reason we call this the cross product matrix is because we do A cross B equals A hat times B. So we take like a geometrical thing, which is the cross product, and we convert it into matrix multiplication. And what you'll notice is that we love doing this in this class. And I think in general, this is nice because when it comes time for doing like any sort of vector calculus, so I'm doing like I want to take a gradient or a Hessian or any of these things. Having an expression that's written up with entirely matrix vector or matrix products is easier for me to reason about mathematically than having things in here like, cross and like in the case of quaternions, quaternion multiplication. Then I brought up the unhat, which is just the inverse of the hat map. So the unhat just takes the skew symmetric matrix and it just maps it back to being the vector itself. And then I introduced this thing, which is totally useless, but gives us a nice similarity between this and quaternions. And then I started this discussion of what do we do when we want to not carry around 9 parameters. So with the direction cosine matrix, I'm storing 9 parameters, but really there's only 3 degrees of freedom in the rotation itself. So why 9? So what ends up happening is that I have 9 parameters with 6 constraints, which gives me 3 degrees of freedom. So really, there's got to be a better, more efficient way to store this information. And it turns out that there like very much is, and that way is storing it as a rotation. So what Euler said was that between any two bases, so before I had n and b, as I drew right here, between any two bases, there's always a simple rotation that rotates me from one to the other. So the way you can think about this is if I take, here's like my phone. If I take a phone in this orientation and in this orientation, it doesn't matter what two orientations I choose, there always exists a clean way to just pierce it with a rod and spin to get from one to the other. And this is not obvious. This was like a big deal. It doesn't matter how these things are oriented for position A or orientation A and orientation B. I can always just pierce it and spin. I guess that's the way I like to think about this. And so what we pierce it with is the axis. So this is R right here. So we pierce it with the axis and then we rotate it the angle. And this gives us the axis angle. So just R hat times theta. And actually, this hat, I'm realizing now, is scary because I defined the hat map as something else. So I'll go ahead and remove the hat. Try not to overload notation. Okay, and then we gave you a way that you can convert between a direction cosine matrix and the axis angle with the matrix log and matrix exponential. But then also, because these are kind of special matrices, there's like, you don't have to use the off-the-shelf version of these things. You can use like rotation-specific ones. So for instance, when I take the matrix exponential of a skew symmetric matrix, there's like a clever way to do this, and it's called Rodriguez formula. And likewise, if I'm taking the matrix logarithm of a 3x3 orthogonal matrix. Again, there's like a special case formula I can use. So there's clever, faster formulas for all these things, but this is still correct, which is nice. So what we talked about is, the axis angle is great for giving us an intuition as far as how do we rotate. It's, I think, conceptually the most simple way to understand a rotation is just pierce an object by some axis and then spin it about that axis. I think that's the simplest. But when it comes time for actually like using this in practice, like in a simulation, it's awful. And the reason why it's awful is because there's a bunch of singularities. So when I'm at no rotation and theta equals 0, what is R, right? It could be anything. So because there's this like ambiguity around 0, it's very hard to simulate this thing about 0, which is useless for us. And then also once it reaches 180 degrees, we have to just cap it off and start somewhere else because like I'm going 180, 180, 180 goes up to 180 and then now starts going down. So having this singularity where there's two different ways to get to the same attitude, that is bad. That gives us a singularity and it makes it very hard to work with. So the solution to all these problems is to just take our axis angle and wrap it up into a quaternion. So we take our same R and theta, and again, I really got to remove these hats. We're going to confuse everybody. So I can take this axis angle with r and theta, and I can just put it into, let's just call it just a length 4 vector. We won't, there's a bunch of like crazy people who love the quaternion math, like in the imaginary form. I don't think it's that useful for just attitude purposes. So just think of this as a length 4 vector, just wrap it up in that, and all of a sudden my life gets way easier. And everything that I can do with rotation matrices, there's an equivalent version of it for me doing it in quaternions. So the way I compose rotations in direction cosine matrix land, I do the same thing for quaternions, but now I use a quaternion multiplication, which is this right here. And then the way I inverted these rotations is earlier I used a transpose when it was a matrix. Here I use a conjugation, which just means I just take my scalar vector, this being the scalar part, this being the vector part. I take that and I just throw a negative on the vector part, and that's how I invert it. And then for multiplication, I wrote it out right here, which again, this is like a special operator that I would write a custom function for, which is fine. But again, when it comes time for taking derivatives and gradients and Hessians and everything, it's really hard to have non-matrix matrix products in there. So what we do is that we convert this special multiplication into just, a function L, and then we just use matrix multiplication. So if I want Q1 times Q2, I can do L of Q1 times Q2, which is just this. Or I can do R of Q2 times Q1, which is just this. Which if you just look at this, the way these three are all related is they're all the top one. I just pull out the certain components I care about and put them on the right. So these are all the same. And then I talked about this weird hat thing that I brought up earlier is actually true for quaternions too. So I have this weird, I used it with a hat bar notation with a quaternion. This is where I take a length 3 vector and I just put it into a quaternion by putting it in the vector component. So literally just 0 and then a length 3 vector. I'll add that A is length 3. Okay, and then this was all office-hour stuff. So now because now I will introduce a little more of this matrix notation. And then I'm going to do just the full comparison of everything we do in direct sine cosine matrices, everything we do with quaternions, and how they're all the exact same, and how we have this nice isomorphism between everything. So the last two things to talk about are, quat math. So quaternion math as matrix math. So earlier we did Q1, Q2 equals L, Q1, Q2, or I can equivalently do R, Q2, Q1. And then another thing we learned is that we can do, actually, did we go over anything else, or was it the only thing we introduced? Okay. And then the other thing we learned is that I can do a quaternion conjugate just by doing scalar negative vector. So if Q, actually I'll do this. If this is my quaternion, conjugate of this is just S negative V, which is the same as me doing the following. This is our T matrix. And the last thing we talked about was that if I can do this A, then how did I do like an upside down hat? Let's see. Okay, right side hat with the bar. I said that this was 0, A. And this is the same as me doing, let's see, there's actually two ways to do this. Okay. Okay, and that concludes the matrix math we need. So all we did is we said that, all right, if we're doing quaternion multiplication, I can do it with these L and R matrices that I defined earlier. And then I said that I can conjugate a quaternion, which is me just swapping the negative sign on V. I can do that with this matrix T. And then this I can do with H. And I can also do the reverse of this. So I can do A equals H transpose of A. And this is me just selecting out the three components. So everything I wrote down here is true. One last thing to note is that I'll put this below here. So a note on the L and R matrices is that these are actually orthogonal. And what that lets us do is that uh, Q1 conjugate Q2, or actually I'll just write it out like this. L of Q transpose equals L Q conjugate. And this is nice to know. Same is true with R. Okay, so here's all of our quaternion math that we would need. Just go ahead and organize this. Okay, and with this, we can start our nice little comparison of everything that we do in one notation, we do in the other. So let's do, oh, actually, one more thing, which is how do we rotate a quaternion? So rotate a vector. So when it came to a rotation matrix, what I said was that I could do this sort of thing. And we also said something weird. So we have option A, option B. And we got two options. So two options, but option A is way faster, and we definitely want to do option A. So option B exists just as a way for us to segue into quaternion stuff, but in general, this is the way to do it. So now let's go through everything we know about the way these things compare, and let's do everything in quaternion math here. And let's see what it looks like. So this is xn. I'll use the quaternion hat thing, equals q nb times xb in this hat version. And then q nb. So you see how everything that I did here in rotation matrix math, I did here in quaternion math. And now let's just convert everything into our matrix math. So this is H. And we'll do this in two steps. And then now I can do the same thing where I just do R. So now I have two quaternions being multiplied. I can just use my same R thing. So R of this times L, or then I can bring this H over on the other side. because H is that weird matrix where it's just zeros and identity, so I can just do H transpose on each side, effectively invert it. And let's see. And there's a few different ways to do this. So which way did I do? Okay, yeah, we're fine. So what are we looking at right here? So what I did was I started out with this expression, which works for rotation matrices. I just wrote out all the math in the equivalent quaternion form, and then I converted that math into our matrix math. And I just used two tricks here and here that you should go and try for yourself. And that gives us this. And what we've seen is that we now have a vector length 3, vector length 3, and then a 3 by 3 rotation matrix right here. And this is cool because this tells us that Q of NB equals H transpose R QNB transpose L QNB H. So just like that, here's how we do GCM from a quaternion. Okay, next thing is kinematics. And this I always think is like such an interesting discussion because everybody has different, I guess, preconceived notions as to why this should work. And it's really not obvious. So translation. So when I'm talking about a translation, I have this, you know, I can take my acceleration as an R3 vector, and I can go ahead and I can integrate this to get velocity. Also an R3 vector, and then I can integrate this to a position. So when it comes to translation, I can integrate all these things. So I take my acceleration, if I'm accelerating an object at some speed and it's constant, I can accelerate that. I can integrate that to get my velocity. And then I can integrate my velocity to get my position. And I can just directly integrate these R3 vectors to become R3 vectors. And everything is nice, makes total sense. And conceptually, we've been doing this for a super long time. So, this is our classic in school as kids. This was, d equals rt. So distance equals rate times time. Just our integral of this over a constant velocity. And then this is our classic d equals 1/2 at squared plus vt. So there's like, we've done these things before and we know these things. We know that we can take translation as an R3 vector and just integrate it up to get velocity and then get position. And now let's talk about what do we do for attitude? Like if I have attitude, I start out with angular velocity, alpha. And then if I integrate up my angular acceleration, what I get is I get my angular velocity. Omega. And then now if I integrate up this, I get nothing. I get nonsense. So I can integrate my angular acceleration to get my angular velocity, but then if I go integrate my angular velocity into another R3 vector, I get just this just random nonsense. Like it's not attitude. It can't back it out. It means nothing. And this is why this is all so difficult. So this is why attitude is such an interesting and complex topic, is because this right here, the fact that we can't just integrate up our angular velocity into some description of position, but for the angular equivalent, this is why everything is so hard. So how do we do this? Well, we have two ways of doing it. So the first is, so first of this, these are called dynamics. So kinematics. And this is just like I have some element of configuration. Config dot is some function of config and velocity. This is what kinematics means. So dynamics is how I get, accelerations as a function of config and velocity. Kinematics is just config as a function of config and velocity. So the way we do this for rotation matrices is that we say, and I can post a proof to this. It's actually pretty straightforward, but here are our direction cosine matrix kinematics. And the bases are really important. This only works if the bases are written like this. If our angular velocity is in a different frame, this doesn't work. But because people just assume these conventions for everything, you'll just see people write this down always, which really bugs me. Is because if you're someone learning this from scratch and you want to learn it for like a robot, for instance, where there's like lots of weird frames, it's important to get the frames right and to understand where the velocity needs to be expressed in. So this is correct. You can always use this. It'll always be correct. But you'll just see people write q dot equals q times omega hat, which is true if q and omega are these things. But if they are anything else, then it's not true. And I feel like it's just easier to write down the notation correctly. So what does this mean? This means that if I have some, doesn't have to be a world frame, doesn't have to be body frame, but that's the most common. These can be anything. So I made no assumptions on N and B. So no assumptions. So I didn't assume that N was a world frame, like N was an inertial frame, B was a body frame. Like I made no assumptions. Just if I have a basis N, a basis B, they are described with this rotation matrix. And this is the angular velocity between them as expressed in the B frame, which is this is what like a gyro on a drone would read. So this is why this is like the most common form. But these are the correct kinematics. And then the quaternion kinematics are very similar. And then I'll do here's just another way to write this. Okay, and this half is interesting. And this, it comes from the double cover thing. We talked about, Zach likes talking about double cover. The idea that every single attitude is covered by two quaternions, Q and negative Q. So you get this kind of double cover property where the space of available orientations is actually covered twice by quaternions because each attitude is described by two unique quaternions. So that's in a way where this one half comes from. But uh, another more, I think, nicer way, and I can post derivations of all these things if anyone's interested, but I don't think it's actually worth going through. But really, the 1/2 comes from. So I'll do 1/2 comes from. This is really where it comes from, like mathematically. Like if I go to the derivation, the way the 1/2 pops up here is that when I created my quaternions, do you remember? There was just like with this one half here and here. So this is where the 1/2 comes from. But yeah, this is true, and you will use this. So now we're at a good point to go do our, I guess, examination of everything. So I'll start on a new page, and I'll do DCM quat. And now I'm going to go and just write out all the things we can do in one and do in the other. And then I'll also do, actually, I'll do kind of three things here. I'll do DCM and then quat, and then this would be quat with matrix math. So the first thing is, how do we rotate a vector? So xn, which again is equivalent to doing this, which I said was dumb, but there's a similarity, so I won't omit it. Quaternion version is xn. And then I can just do the same thing in matrix math, just going h xn equals L Q H XB, and then uh, I'll do what I did earlier. Let's do this. Okay, so that's the first line. Next line, this is how we compose rotations. So Q AC equals Q AB QBC. And in quaternions, I do the exact same kind of stuff. It's now using a new type of multiply. And then with matrix math, same thing. Okay, now the third thing we'll do is how to actually transpose these things. So Q AB, wow, that was a terrible B. AB equals Q of BA transpose. Q of AB equals Q BA conjugate, which in matrix math is just, what's it, AB? This T matrix, which I define T here, T. Okay, and the last thing we got is our kinematics. QNB equals QNB, which is just okay. That was a lot of writing. What we're working towards here is that do you see how this is all, it just looks so similar. So this is just like, for our convenience of giving you some practice on how we actually do like matrix or quaternion math using matrix stuff, which I think is useful. Like certainly for driving these things, it's very useful because it's way easier for us to manipulate matrix equations than it is quaternion math equations. But what's nice to see is that between here and here, there's just like this very strong similarity between everything. And everything we can do with rotation matrices, there's an equivalent version of this we can do with quaternions. And I think that's like one of the main takeaways from at least this class with respect to attitude, is that all these things are well defined. There's ways to do everything in every parameterization we use. And it's important to like always know these things and keep them in mind. So now I was going to talk real quick, not going to spend too much time on it, but other three parameter attitude. Okay. So we have a few options here. So the first one is a Rodriguez parameter. The first thing actually I talked about earlier was axis angle. So axis angle was just this, I have literally an axis multiplied by an angle. Rodriguez parameter, this is where I take my quaternion. So I do vector over scalar. So if I just take my vector and divide it by a scalar, what I get is like a nice R3 vector. This is also called a Gibbs vector. And this is, as you can see, so if I look back at my, because you remember quat, this is cosine theta over 2, r sine theta over 2. When theta equals 180 degrees, the scalar part of the quaternion is 0. So the scalar part of this quaternion goes 0 at 180, which means that if I am trying to be sneaky and only store my quaternion using 3 parameters by just taking the vector and dividing it by the scalar, I'm going to divide by 0 at 180 degrees, which is okay. It's actually like, it's fine to use this for things that are less than 180, and you see this used all the time. Um, like Euler angles have far more singularities, and they're used, like they're ubiquitous. Everybody uses Euler angles. So this is singular at 180, and that's bad. And then I can go from I can do quat Q from Rodriguez parameter. And I like using G. This is just normalize 1G. So here's how you go from a quaternion to a Rodriguez parameter. Here's how you do, sorry, this is Rodriguez parameter from quaternion. This is quaternion from Rodriguez parameter, and this is also called the Cayley map. And let's see, I think the last thing I'll bring up is MRP. So modified Rodriguez parameter, I'll call this P. And there's a few different ways to define P. So P is R times tan theta over 4. Let me just check on this before I give you guys bad information. Um, yep. So R times tan. However, it's also equal to, and you can go through and prove this with your like trig identities if you want to, but I wouldn't. So here's how to get there from axis angle. Here's how to get there from quaternion. And then there's a formula you can easily look up that takes you from modified Rodriguez parameters to quaternion. So I want to convert that. And this is, importantly, singular. So I have pushed my singularity, where it used to be at 180, I have now pushed it to 360. And this is when s equals -1. Actually, I think it's worth doing. S equals. Okay. And why do we use one of these versus the other? Okay. So there is nice. Okay. So we've been over this q dot as a function of nice, well-defined, nice, no trig. Then q dot, which is our quaternion kinematics, nice, no trig. And then we have axis angle. And this is just awful. Don't use. Okay, so of our additive representations, here's all the kinematics just from like a very high level. Uh, Doing kinematics with a rotation matrix, nice, well-defined, very easy. Quaternion, nice, well-defined, easy. This is like horrific. Can't emphasize enough just how bad this is. Never do this. And then nice, nice. And then what are the trade-offs of these things? Like we have like just enough time to do this. Should be a nice thing to end on. So we got DCM, quat, axis angle, Rodriguez parameter, modified Rodriguez parameter. And then so we'll do params, 9 parameters, 4 parameters, 3, 3, 3. singular, no, no, 180, 180, 360. So yeah, I guess that's probably enough to put in here. There's like a lot more you could put in things like this, but kinematics. So at a very high level, here's the stuff that we'll see in this class. So as you can notice, if I'm ever just doing simulation, so no optimization, no anything, I just want to simulate a system, this is our winner. Use this to simulate. If I'm doing general control stuff, like with a drone that's not doing crazy flips, so what we did in your homework, this is, I think, our like best option. Three parameters, there's no constraints. It's singular at 360, so unless I'm doing a full spin, I won't run into trouble. And the kinematics are nice and well defined. So yeah, in the last few minutes, I'll go ahead and stop the recording now.